All right, with that housekeeping out of the way, again, thank you for joining us and welcome to our June Twin Ports Climate Conversation. Climate Conversations are quarterly convenings here in the Western Lake Superior region aimed to improve climate change communication skills, climate change related data collection and sharing, and to support climate adaptation broadly in our area, the Duluth Twin Ports region. These events are coordinated by the Twin Ports Climate Conversations planning team and staff from the Minnesota Lake Superior Coastal Program at the Department of Natural Resources, the 1854 Treaty Authority, University of Minnesota Sea Grant Program, and the City of Superior. So we thank you for joining us, and thank you to the other members of the planning team for their support of TPCC and to make these events possible. You can learn more about this series and view past recordings on our website. I'll be putting a link in the chat for you to view recorded webinars that date back to 2020. This group has been around in existence since 2015, but you can look in a back archive of our previous events and webinars at that website in the chat. Today's webinar should be a really great one. We're really excited to welcome Dr. Susie Clark, who'll be sharing about a recently launched tool, MN CliMAT, a tool for visualizing different climate futures at a local scale across Minnesota. And Dr. Clark is a climate adaptation and resilience extension educator with the University of Minnesota Climate Adaptation Partnership. She studied environmental science at UCLA and earned her PhD in physical oceanography from MIT Woods Hole Joint Program in Oceanography. And prior to joining the University of Minnesota Climate Adaptation Partnership, or MCAP as you might know it, she's lived and worked in a variety of places, from Southern California to Germany to New England, and has researched topics including harmful algal blooms, renewable energy, and climate change. As a climate adaptation and resilience extension educator with MCAP, she leads applied research and educational programs focused on adapting to climate change in Minnesota. With a particular focus on water resources. So it's great to have Susie joining us here today to share all about this tool. I'm going to stop sharing my screen and let Susie take over. And with that, please give Susie a welcome to TPCC, and really excited to hear about the MN CliMAT tool.
Thanks, Madison. Every time someone gives that brief bio, I think, it could probably be briefer, but thank you for the introduction. So as Madison queued up for you all, today I'm going to be talking about our new, recently fully publicly launched tool called MN CliMAT, which stands for the Minnesota Climate Mapping and Analysis Tool. So today I'll give you a little bit of an overview, and please excuse me in advance. I am recovering from a recent illness and I've got some remaining congestion. I will try to avoid clearing my throat too much. So today, we're going to give you an overview on MCAP, the University of Minnesota Climate Adaptation Partnership, and what climate change means for both Minnesota and Wisconsin. Then I will cover a little bit of the basics of climate data and climate models, give you an overview of MN CliMAT and how it works, and show you a little demonstration of using MN CliMAT in action. And then I'll end with opportunities if you would like to learn more and provide hopefully plenty of time for questions at the end. So before we get started, I would like to actually launch a poll and learn a little bit about who you are. So give me just a moment. And some of the questions we want to know first where you're tuning in from. So just a city and state is fine, or even state if you're not comfortable giving city. I'd like to know the balance of Minnesota and Wisconsin viewers on this call. What sector you're affiliated with, or what you consider yourself to be affiliated with, and your familiarity with both climate adaptation and climate data. So I'll go ahead and launch that, give you all a couple of minutes to respond, and then I'll share it with you after I've gotten some responses. So I'll give you a little teaser as the answers are rolling in. We have quite a few people joining us from state government, a couple from federal and municipal governments and NGOs. Many people saying that they understand what climate adaptation is, and a little bit fewer than that saying they both understand it and they practice it in their professional or personal life. That's great. Love to hear that. And most people are answering that they are either somewhat or very familiar with climate data. We'll give just another 30 seconds for people to finish responding. All right. Excellent. Thank you all for taking a moment to answer these questions. Now, something I didn't realize is that I wouldn't be able to see the city and state right off the bat, but so I will make sure that I address both Minnesota and Wisconsin. I'll take a look at those results later. On the second question, as you can see, the largest answer for the sectors was for state government. And the majority of you indicated that you either know what climate adaptation is, or you know it and you use it in your professional or personal life. And that many of you are either somewhat or very familiar with climate data. For those of you who are not at all familiar or not very familiar, don't worry. The purpose of this webinar is to get us all on the same page. So first, what is MCAP, which is the University of Minnesota Climate Adaptation Partnership? So we are an organization housed at the University of Minnesota that is simultaneously situated in the research arm of the university and the extension arm. So we both conduct climate research and communicate the research. And we do so through a team of extension educators like myself who create climate adaptation educational programming. And our goal is to create a team of people across the state, across a variety of different sectors. So I am focused on water resources. I have a colleague who's focused on agriculture, a colleague focused on tribal food systems, and soon to be a colleague focused on public health. Our mission is threefold. We partner to support thriving communities and landscapes through collaboration, capacity building, and advanced climate-informed decision-making. So collaboration, one of the main ways that we achieve this is our biannual Midwest Climate Resilience Conference. We hosted our first one last October, but the tradition of hosting an annual adaptation conference actually goes back over a decade with MCAP, but we have now made it a more regional conference to try to create those spaces where people can share their successes and their challenges in climate adaptation. Capacity building, this often encompasses training opportunities or workshops because we recognize that climate data are really only the first step in actually implementing climate adaptation. We want people to also learn the skills about how to use this information. And underpinning all of this is our cutting edge research that advances climate-informed decision-making. So we believe very strongly in the idea that understanding climate change is a key component to adapting to it. And we want to produce the information necessary for people to understand their climate risks. And this little screenshot on the right is actually a screenshot from MN CliMAT, which I will show you later on in the talk. This is only actually a subset of our team. We have many students and interns who are working with us as well, but for privacy reasons, we don't put their pictures up here. But our team encompasses our director, Heidi Roop, two associate directors, a climate scientist, a GIS specialist, communication specialist, curriculum manager, and a host of extension educators. So we have the capacity on our team, as I said, to both conduct the research and to disseminate the research to the broader public. And we are offering, hopefully, the job to our soon-to-be public health extension educator this week. So hopefully that picture will fill in shortly. And our work is varied. We have in the top left, high resolution climate projections that underpin MN CliMAT, but that's not the only thing we do. We also have our dedicated extension programming that teaches people concepts such as how to make decisions when there is such incredible uncertainty. We do a lot of research on networks and communication. How do people work with each other on climate adaptation? How do they communicate with each other? We do, as I mentioned, public engagement and training. We also engage with state and federal entities. We partner with federal agencies such as USGS, US Fish and Wildlife Service, as well as state agencies such as the Pollution Control Agency and the DNR. So that's what we do. But something that you're probably really interested in is what does climate change mean for Minnesota and Wisconsin? And I've added Wisconsin into this talk, although I am officially an educator for Minnesota, because I know that we probably have some people tuning in from northern Wisconsin for this talk as part of the Twin Ports Climate Conversations. So I just want to let you know that my expertise is much more focused on Minnesota, but a lot of the changes we are observing and projecting for Minnesota apply to Wisconsin as well, particularly northern Wisconsin. So on average, the climate is getting warmer and wetter. I don't think I need to convince anyone of this year. We had an unusually warm winter, one of the warmest on record, and we are having a wetter than average spring. It feels like it's been raining nonstop for several weeks. And actually, the 10 wettest and warmest years on record in Minnesota have all occurred since 1997. 2016 was the warmest and wettest year on record. No other warm year was quite as wet, and no other wet year was quite as warm. And it's similar in Wisconsin. The wettest 5-year period on record, so since 1895, was 2015 to 2019. We've also observed a 13% increase in the heaviest rainfall of the year here in Minnesota, meaning that each year the heaviest rainfall now holds 13% more water than it used to. And similarly in Wisconsin, these extreme precipitation events have become more frequent in the last couple of decades. And lastly, across the Midwest, the growing season, so the time between the last frost in the spring and the first frost in the fall, has lengthened by about 2 weeks since the mid-20th century. Here in Minnesota, average annual temperatures have increased by almost 3 degrees Fahrenheit since 1895. But what's interesting is that there are spatial and temporal patterns to this. So it's not a consistent change in time or space. These maps show you the change in average annual temperature on the left, the change in winter lows in the center, and the change in summer highs on the right. And what I want to draw your attention to is that the largest observed change has been in the north in those winter lows. So those famous winters that Minnesota is known for do not happen the way that they used to. On average, those nighttime lows in winter have warmed by over 7 degrees Fahrenheit in the past 125 years. Similarly, in Wisconsin, the average annual temperature has increased by 2 to 3 degrees Fahrenheit since 1900. So these maps are taken from Wisconsin DNR and the Center for Climatic Research at the University of Wisconsin-Madison. So on the left, we have annual average change since 1950. These are a slightly different time period. In the middle, we have change in winter lows, and on the right, we have change in summer highs. So while the average annual increase has been about 2 degrees Fahrenheit, the winter lows, particularly here in the northwestern part of the state, have increased by 6 degrees Fahrenheit. And we have not yet observed a significant change in summertime highs. Also across the Midwest, the last spring freeze is happening earlier and earlier. So this map shows you what is defined as the Midwest region by the National Climate Assessment. And you have each individual county, and everywhere that a county is yellow to red, the spring freeze has happened earlier and earlier over time. And so you can see that this is a pattern across the Midwest. Also across the Midwest, transitions from wet to dry extremes are happening more quickly and more frequently. This is another thing that I don't think I need to try to convince people of. We had a particularly dry winter. I live walking distance from Minnehaha Falls in Minneapolis, which is a famous local spot for people to go see a nice waterfall. And in February, I predicted they're going to be completely dry by June. It's like they were already almost bone dry in February. And we have had such rain over the spring that they are flowing higher than I've ever seen them, and we're under a flood watch. So these transitions from these wet to dry extremes, they're happening more often within a given year than they used to, and they're also happening faster than they used to. And we expect this trend to continue. In the future, we expect that Minnesota and Wisconsin's climates are projected to continue to warm, and we expect this warming to not only occur in the winter, we expect it to extend to the summer. And they are expected to become wetter on average. That's an important caveat because most of the increased precipitation we project will happen in winter and spring, whereas summers we expect to become more dry. And that relates to the third point about being more extreme. So not only do we expect stronger rainstorms and hotter and longer lasting heat waves, but we also expect more rapid transitions between these extremes. So what do we do about it? Oftentimes, the public conversation is focused on mitigation, which is how we can reduce climate change itself. How can we reduce our greenhouse gas emissions, and how can we stop climate change from happening? But we also need to consider that we have committed to a certain degree of warming regardless. Even if we were to completely stop emitting greenhouse gases tomorrow, the Earth would continue to warm. So we need to also think about how it will affect us, and we need to adapt our practices to reduce that associated risk. So adaptation can affect every sector. This is just a little sampling of icons for you to kind of get your juices flowing, but it can affect engineering, forestry, water resources, public health, that's a big one, infrastructure, and agriculture. And so we need to think of all these different sectors when we think about climate adaptation. But very important is that risks are locally specific. So we need to understand the risks we face in our own localities in order to better prepare for them. So this is a map of the projected change by 2050 in average annual loss in dollars due to all types of flooding across the US. And everywhere we have values that, well, most of the country has values that are greater than zero. So we expect increased loss due to flooding. But that risk is really concentrated here on the Atlantic seaboard and the Gulf Coast. So you would be ill-advised to take projections for Florida, for example, and apply them up here to Minnesota and Wisconsin. And so we really need local projections that help us understand our risks here so that we can better prepare for them. And this is where MN CliMAT comes into play. So the Minnesota Climate Mapping and Analysis tool helps people across the state see how climate change will affect them locally. This is just a screenshot. I will actually share the tool later and click around on it a bit so that you can see that. But it gives projections at the 4-kilometer scale, which means that individual towns can see projections for how climate change will affect them. So I want to make sure that we all understand where these projections come from, because it really affects how you interpret what they mean. So first, there are two fundamental types of climate data. We often talk about historical climate data, which is what you might find in a farmer's almanac, for example. These are calculated from observations taken over many, many, many years that are then averaged together. What we're talking about with MN CliMAT are climate projections. These are simulated by computer models. Both historical data and projections include long-term averages, so 20 to 30 years, of the characteristics of a region's climate, such as precipitation, temperature, and humidity. And so, as I mentioned, we are focusing on climate projections. That's what we have in MN CliMAT. How do we get these climate projections? Global climate models, or GCMs, as they're sometimes called, use established math and physics to represent the Earth as an integrated system. So oftentimes it can feel like global climate models are a black box. Scientists put some numbers in and they get some numbers out, and who knows where they came from. But actually, they simulate the physics, chemistry, and biology of the Earth using well-established, well-understood mathematical equations. And they do so by breaking the Earth up into all these little boxes, like you see here on the left, calculating what happens within a box, and then calculating how the boxes communicate with each other. They also try to create common scenarios to help us simulate a variety of futures. So in theory, you could have almost infinite number of potential futures, but in reality, there are some that are more likely than others. And there are actually dozens of global climate models across the globe. And so what we need to do is try to make sure they are creating apples to apples simulations of the future so that we can compare their output. And that's what these scenarios are for. So in the latest generation of global climate models, we have shared socioeconomic pathways, or SSPs. They consider both how much greenhouse gas we emit, and how they are emitted. So what are the societal choices that we make as a global society to reach these greenhouse gas emissions? There are 5 scenarios. The first one, sustainability, is also sometimes called the green road. This assumes that the global community works together, international collaboration leads towards rapid advancements in quality of life, and we do so using renewable energy and capturing carbon. SSP2 is sometimes called the middle of the road. This is the scenario that assumes the continuation of historical trends. SSP3 is regional rivalry, also sometimes called a rocky road. And this is the scenario where countries and nations become more interested in their own interests rather than in international collaboration at the risk of advancements in renewable energy and quality of life and education, et cetera. SSP4, inequality, is also called a road divided. And this refers to the fact that in this future, half of the world's nations rapidly advance, kind of akin to the sustainability route, and the other half of the world is left behind. And lastly, SSP5, fossil fuel development, is also sometimes called taking the highway. And in this scenario, we rapidly invest in fossil fuels in order to improve quality of life around the world and to advance technologically and to improve education and public health, et cetera. But it is all done with fossil fuels. So the ones that we have for you all in MN CliMAT are SSP2, 3, and 5. And we chose these three to provide a range of potential futures. And I'll show you what I mean by that on the next slide. So the purpose of SSPs is to give a range of potential futures. On the left, we have different carbon dioxide emissions for the different scenarios. So we have the blue SSP1 down here at the bottom, and we have red SSP5 up here at the top. Remember, SSP1 is sustainability, and SSP5 is fossil fuel development. These translate to changes in temperature. So again, we have 5 different scenarios here showing the change in temperature from just pretty recently, a couple of years ago, out to the year 2100. SSP1, which is the sustainability pathway, still projects an average global increase in temperature of about 5.4 degrees Fahrenheit. This may not seem like much because here in the upper Midwest, we can often get swings in temperature of 15 to 20 degrees over a couple of days. Actually, that happened this weekend. But on terms of the long-term average of climate, 5.4 degrees Fahrenheit is actually impactful. And then the upper bound is SSP5, that fossil fuel development pathway, projects a potential increase of 9 degrees Fahrenheit of the global average temperature. And again, we have SSPs 2, 3, and 5 on MN CliMAT, so you can see this range and you can really understand how the different scenarios result in different impacts. And also, just as a side note, SSP3 is the pathway that the global climate modeling community increasingly agrees that we are currently on. That is the regional rivalry pathway. And you only have to pay a little bit of attention to global politics to understand why that seems to be the path we're on. So these global climate models are really powerful tools, but they make projections for the entire globe. The best that they can get is at about a 60-mile scale, which means that you would have one estimate for all of the Arrowhead region of Minnesota, or you would have one estimate for the entire Twin Cities metro. When really we know that changes can be much more varied than that. So this image here shows you on the left something that a global climate model might see. This isn't real data. These are just colors to illustrate a point. And on the right, this shows you what you might see with a regional climate model. Scientists use a process called downscaling that basically increases the detail that we can see with a model. I don't have time to go into the details of downscaling, but I find it particularly interesting. So if you're interested, please feel free to contact me after the webinar. Happy to nerd out about that with you. But this is how we developed the data for MN CliMAT. And this is why our resolution in MN CliMAT is so high, roughly 2.5 miles. So you're all probably thinking, great, thank you for the background information. That's not why I'm here. What is MN CliMAT? This is our online tool. It is publicly available. It is free to use. The only thing we ask is that you acknowledge a disclaimer when you first go to it. And the first time you download some information from the website, we ask you for basic information such as where you are, like what city you're in, and your email. And this is only to send updates if there are changes to the tool. It provides statewide resolution, high resolution projections at the 2.5 mile scale for multiple future time periods. We have the 2050s, the 2070s, and the 2090s. We have 3 different emission scenarios, as I mentioned, SSPs 2, 3, and 5. So middle of the road, regional rivalry, and fossil fuel development. And we also have, I believe, over 35 different variables, including everything from temperature and precipitation to more impact-related variables such as soil moisture. So the 3 future time periods, as I mentioned, are mid-century, late century, and end of century. Remember that climate data are averaged over 20 to 30 years. So we have actually run the simulation for 20 years, but what we provide in the tool is the 20-year average. So mid-century refers to 2040 to 59, late century is 2060 to 79, and end of century is 2080 to 99. We also have historical simulations for comparison with those future projections. As I mentioned, we have 3 different emission scenarios, SSP 2, 3, and 5. If you are more versed in the climate modeling world and you remember the previous generation of climate models, they had RCPs, representative concentration pathways. So the reason why you have 3 numbers here is because SSP2 is a close analog to RCP 4.5, and SSP5 is a close analog to RCP 8.5, and SSP3 falls in the middle. If you're not that interested in climate modeling, you can just forget that comment and remember SSPs 2, 3, and 5. So as I said, we have over 30 variables in a variety of categories: precipitation, temperature, humidity, soils, and lakes. I'll go into those with a little bit more detail. So we not only have projections for precipitation values, but also thresholds of precipitation and their intensity. So we have projections for the number of days with precipitation greater than 0.01, so essentially any precipitation, 1 and 2 inches. We also have projections for the longest dry spell, so time without measurable precipitation. And we also have estimates for maximum amount of precipitation in 1 day, 2 days, all the way up to 7 days. Also, precipitation is not only rain, it comes as snow. So we have projections for snow cover and the number of days with snow cover. And this has implications for all sorts of different fields. So it can help you understand future flood risk, future drought risk, risk to infrastructure, and also the effects on recreation. So snow cover, how does that affect my ability to go cross-country skiing? How does that affect the populations of key species such as moose? And how does that affect our needs to manage our infrastructure? We also have a variety of different temperature variables. So we have daily maximum, average, and minimum, but we also have projections for the number of days that stay above a certain temperature. So for example, the number of nights that are above 70 degrees Fahrenheit. This is very relevant for public health. We also have projections for number of days where the temperature is below a certain temperature. So number of nights below freezing, for example. And we also have projections for extreme heat events. So the number of days that exceed 90, 95, and 100 degrees Fahrenheit. And the most obvious application of some of these variables is public health, as I mentioned, but extreme temperatures can also affect infrastructure, such as roadways. They can have implications for disease and pest pressure because diseases and pests persist better in the winter when it doesn't get as cold. And they can have implications for crop success and vitality because relative humidity affects the evapotranspiration of crops. And speaking of crops, we also have impact variables for soils. So soil temperature and moisture at 4 different depths. And also we have some variables for lakes. So the projection of how much of a lake surface is frozen and the temperature at the lake bottom. We currently have 70 odd lakes across Minnesota in MN CliMAT. This is an issue of that resolution that I talked about earlier. If the lake is too small, then we can't capture it directly with our model. But we do have a pretty good range of lakes across the state, north to south. And these have implications for agriculture, forestry, fishing, recreation, safety, such as ice thickness, you name it. And you can also average these different variables over a variety of time periods. So you can average it over the whole year. You can average it over the growing season. You can average over specific seasons, and you can average monthly. And this is really relevant for things that are not projected to change uniformly. So remember I said that precipitation is expected to increase on average, but we expect more increases in spring and winter and actually a decrease in precipitation in the summer. You can look at that by looking at the averages over the different seasons. So at this point, I'm going to actually stop sharing this screen and I'm going to bring up the tool itself. So Madison, if you could please drop the link for the tool into the chat.
It's there, Susie, so folks can
Thanks.
copy that link and put it into your web browser.
Thank you. Let me pull up the tool very quickly. And also internally, we still often just refer to it as the tool rather than MN CliMAT. So if you hear me say that, then that's why. Okay. I apologize. This is what happens when you use full screen. There it is. All right. So when you go to act.climate.umn.edu, this is what you see. It is a map of Minnesota with a lot of text on the left, a information box at the bottom, and a legend on the right. And you can actually get information from this in a couple of different ways. So if you click on Create Map, you have this menu here on the left that allows you to choose a variety of different parameters to change what you see on the map. So you can choose a variety of what we call areas of interest or AOIs. We have many that are predefined. So you can choose any of the counties across the state. So for example, here on the North Shore, in the Arrowhead region, you might be interested in Cook, Lake, or St. Louis counties. You can look at climate divisions. So we have 9 climate divisions in Minnesota: North, Central, and South, and also West, Central, and East. But we also have some more specific areas of interest. So you can look at individual state parks. If you're interested, for example, in, let me zoom it in a little bit so that I can actually click on these. For example, you can see projections for Split Rock Lighthouse. You can also choose it in this drop-down list if it's too difficult to choose on the map. And so then you have projections specifically for Split Rock Lighthouse. You can also choose state forests. There's a variety of those. Watersheds from the state's One Watershed, One Plan unit. We have tribal government areas as well. So you can look at projections for just Fond du Lac or Grand Portage. We also have, because I know the 1854 Treaty Authority is part of TPCC, we have those areas as well, the Treaty of 1854 and 1837. Also, I want to acknowledge that we are aware there are many more ceded territories that fall within the state of Minnesota. So that's one of the things we would like to include in the tool in our continued work. And then the last is electric service areas, if you're more a utilities inclined person. And Wisconsin, I have not forgotten about you. So let me go ahead and clear my AOI entirely. We have the information from Minnesota here on the homepage, but we actually have data for much more than just the state of Minnesota. So if you scroll down to the left, automatically selected is hide data outside of Minnesota. But if you unselect that, you will see that actually the majority of Wisconsin, sorry, Door County, is included in this as well. All of these data are valid and usable and can be downloaded as well. The only challenge is that we do not have predefined AOIs for Wisconsin. However, you can draw your own. So here on the left, you can choose to draw an AOI with a rectangle, for example, and I can draw a rectangle that encompasses the area that I'm interested in. You can also upload your own shape files in order to average over areas that you are most interested in. Once you've selected your AOI, let's go back to counties and I'll select St. Louis County. You can choose if you want to see modeled values or the difference from historical values. So I want to be careful to say here that the difference is between projections from the model and historical simulations from the model. And that's a best practice in climate modeling. I can answer the more questions about that later if you'd like. So let's go ahead and start by looking at the modeled values. Here's where you can choose what time period and what emission scenario you're interested in. So you can look at the intermediate emissions, which is SSP2, that middle of the road scenario. You can look at high emissions, SSP3, regional rivalry, or you can look at very high emissions, which is SSP2 or the fossil fuel development. You can also look at the mid-century, 2050s, late century, roughly 2070s, and end of century, roughly 2090s. So automatically selected here is the end of century very high emission scenario. So this is sort of an upper bound of what we would expect in terms of change, because the changes increase with time towards the end of the century, and they also increase with the higher emission scenarios. You can choose your variable. As you see, there are a whole host of variables to choose from, and you can choose over which time period you want to average. So what I have selected here are the number of days that we project. Sorry, this is the average, the daily maximum temperature averaged over the year at the end of the century under a very high emission scenario. So in St. Louis County, by the end of the century, we project that average daily maximum temperature is going to be about 59 degrees Fahrenheit. I don't know about you, but I actually don't really know off the top of my head what the average over the year daily maximum temperature is where I live. What I find to be more intuitive is how will temperature change. So I'm going to go to daily average temperature and I'm going to click the difference. And to me, this is a much more meaningful map. So now I have the average change in daily average temperature in St. Louis County at the end of the century under a very high emission scenario. And we project that daily average temperature will increase by almost 12 degrees Fahrenheit relative to historical simulations in this time period and in this scenario. But you can also look at a different emission scenario. So watch this number right here in this box. That's what's going to change. It'll summarize everything for you. So let's say I want to look at the intermediate emission scenario. Now we project that daily average temperature will increase by about 7 degrees Fahrenheit. Or if we look at SSP 370 at the end of the century, we project daily average temperature will increase by about 9 degrees Fahrenheit. You can also look at different time periods with the same emission scenario. So now if we consider all very high emission scenarios, but different time periods, mid-century, we expect about a 4.5 degree increase. Late century, this number has changed to 7.3 degrees. And end of century, we're back at that almost 12 degrees Fahrenheit projected change. Some other variables that might be particularly interesting to this crowd are number of nights below freezing or number of days with snow cover. Those you see some really interesting changes towards the end of the century. So if I look at number of days with minimum temperature below 32 Fahrenheit or below freezing, and now I'm going to go back to the modeled values. You see these really interesting spatial patterns where the northeast corner of the state has the most number of days with a minimum temperature below freezing. And so at the end of the century, we expect there to be about 107 days that go below freezing. But if you go back in time, so late century, it's 128 days, and mid-century, it's 144 days. So I could click around on this map forever. There are 14,000 potential different maps you can make, combining variables and time periods and emission scenarios and areas of interest, you name it. You can have a lot of fun with this. I also want to point out that you can download data as a spreadsheet rather than as a map. So that allows you to select and compare multiple time periods, multiple emission scenarios, and multiple different variables. And if you want to download your map, you go back to this Create Map tab, scroll to the bottom, and you can download it as a PNG. So what I think could be very useful at this time is I'm curious what variables you all might be interested in. So if you have a variable that you would like me to pull up, a specific projection, or a time period or emission scenario that you'd like me to pull up, please drop that in the question and answer. And you remember you can upvote and downvote other people's suggestions so we can see which ones are the most popular requests. I will pull up briefly these variables again. So there are precipitation, precipitation intensity, snow, humidity, temperature, temperature thresholds, soils, and lakes. So I'm going to give about 30 seconds to a minute. If you have any particular requests, please drop those into the Q&A box and we can pull that up for everybody.
Hey, Susie, while we are waiting for folks to upvote and answer, put some variables into the Q&A, would you mind answering a quick question from Kevin?
Absolutely.
Okay, so this question came in while you were giving your overview, and Kevin asks, are there some categories of climate data whose projections have more or less confidence? I absolutely trust that it's based on well-established science, but does CliMAT report confidence levels in the projections? Are we as confident about precipitation projections as we are about something like temperature or vegetation succession, etc.? Or is it like scope 1, 2, 3 emissions reporting where some categories are known to be less confident?
This is a very relevant question. We get this question quite often, and it's a very tricky one to answer. I'll do my best. So we often have people asking if we can put confidence intervals on these projections. And what you have to understand is that there are multiple sources of uncertainty in projections. So yes, we could put confidence intervals on the numbers that we have created. So we have run enough simulations, we have enough data points that we can run statistics. So we could say we are 95% confident that precipitation in this area at the end of the century under this scenario is going to be X, because 95% of our simulations fall within this range. So we could put those intervals on there and we could put those values. But something to remember is that towards the end of the century, the greatest source of uncertainty in our projections is actually in which scenario will happen. And that is not something that's decided by the climate models or even by science. That's something that's decided by society. So when we are trying to understand likelihood and confidence, we have to keep in mind that we're still not quite sure what society is going to do. One way to kind of get around some of this, if you're a more savvy user, if you have more comfort with working with these kinds of data, under advanced options, you can actually select which model to see. So the default is the ensemble, because that's actually best practice in the climate community. These are all a bunch of jumbles of letters and numbers. These are just different models from modeling groups around the world. We do not recommend using the results of a single model. However, you can compare them. And if you find that the models are pretty tight in their projections, then that means we have more certainty in that projection. If the models have a really big spread in their projections, then that means we have less certainty. I hope that helps to answer the question.
Thanks, Susie. And it looks like we've got some variables coming in, so maybe you can take a look at those, or I can read them out loud if that's helpful.
I've got them up here on the Q&A
Great.
box. Let me just move that out of the way a little bit. So proportion of lake surface frozen is one of the questions. I'm going to go ahead and just keep this whole map up here. I apologize, I'm not on my very large screen, because then you'd be able to see much more detail. But so one thing I forgot to mention is that these letters here in the brackets at the end tell you over which period you can average this particular variable. So proportion of lake surface that is frozen can be averaged over the year, over a season, or over a specific month. So this is now bringing up all of these different lakes. You can see that our model actually extends quite north of the border with Canada. And it's showing you the proportion of a lake that is frozen in the top 2 inches. So here in Red Lake, we've got 0.4 to 0.45, so 40 to 45%. Numbers change out here over Lake Superior. I can also look over winter. Obviously, you're going to have more of the lakes frozen in winter. You can see that the 0.9, so about 90%. And if I were to click on summer, none of the lakes are frozen. Snow cover, I think that's a very interesting one. Let me go ahead and look at the difference in snow cover. I'm actually going to reset all of these. It's a quick little button you can select if you want to just take it all back to the beginning. So I'm going to look at the difference. Let's stick with end of century, but I'll do the regional rivalry scenario. And we want changes in the number. How about changes in number of days with snow cover depth greater than 1 inch? So essentially the change in the number of days when we project any sort of snow cover. So this is averaged over the course of a year. the annual number of days with snow cover depth greater than 1 inch in St. Louis County is projected to decline by 35.5 days by the end of the century under a high emissions scenario. So essentially a month with one less month with snow cover on the ground. If I change that to the very high emissions, that number goes up to 45.5 days. And the fractional number is because we're averaging across multiple climate model simulations. So a month and a half fewer days with snow cover on the ground by the end of the century in a very high emission scenario. We have a question here about dew points that are representative of tropical air masses. We do not actually have dew points as one of the variables in the model. We do have humidity and temperature, however. So that would be a fairly straightforward thing to answer. I'm actually going to go ahead and click these as answered as I go so I don't lose my place. We had somebody interested in precipitation intensity. That's an interesting one as well. Let's go ahead and keep it at differences. Precipitation. What I find really interesting about precipitation is if we look at the percent difference from between future and historical simulations, again, this is still end of century, very high emissions. We see projections of increase in temperature across the region. However, this is the annual average. If I change my time period to summer, here you can see the decrease that I was talking about. Everywhere that it is white to red, we expect precipitation to actually decrease relative to the historical. But if I change it to spring, then we see in some parts of Minnesota, we see up to 50% increase in precipitation in the spring over the historical. So that's where those seasonal averages can become really important. All right, so I have a couple more questions related to the tool, and then I'll stop sharing and I'll get to the more conceptual questions. Wind quality and quantity in the mix. So wind is definitely included in our simulations. However, we don't necessarily have wind speed in the tool at this time. Apologies for that. I can talk to our climate modeler. And then one person was interested in seeing soil. So we have, and here I need to clear my variables so that I can choose the timeframes that I want. Oh dear, what's going on here? There we go. So let's say you're interested in soil moisture at the surface from 0 to 10 centimeters. I myself am not very well versed in soils, but this is the soil water fraction by volume at the surface, so 0 to 10 centimeters depth. And every map that you want to create will have what's here in map form will be written down here as well in text form. And again, if you choose a different scenario, you can see the numbers down here change, as well as the text within the box. So I'm going to go ahead and stop sharing. You all have the link. I encourage you to play around with that a little bit. But I also encourage you to learn about some of the opportunities we are creating to train people in the use of MN CliMAT. So Madison, do you mind if I just keep going through the questions?
That's great, Susie. You can go ahead. Otherwise, I'm happy to read them out for you, but you've got it.
Kenny actually answered the question about winds on my behalf. Thank you, Kenny. I'll just read them out for everybody. It says the downscaling technique they use models individual weather events the same way a high resolution weather forecasting model does, but it would take intensive analysis to determine something like tree damage. And this touches on a couple of very important points. First is that the model that we use is the weather research and forecasting model. So it is actually a model that's used to forecast weather events. The difference is how we use it. So we run it for many years and we average across those years. And also when you're trying to forecast weather, you start by telling the model what the weather is today, and then you let it run forward in time. When you're trying to forecast project climate change, you start with those changes in emissions. You start with those scenarios, and then you let the model run. So the way you use and interact with the model is a little bit different, but it is at its core a weather forecasting model. And often we get questions about these sort of impacts related projections. For example, crop yield is a really common one, or flooding is another really common one. And these often require additional analysis beyond what we do with MN CliMAT. So to get the data in MN CliMAT, we ran a climate model, which can tell you things like precipitation, temperature, and humidity. But then you need to do another series of analysis to think about how those changes to temperature and precipitation translate to things like crop yield and tree damage. Julie asked which sectors and roles we anticipate will be using this tool or should be informed of it for their work. I click answer live. So we hope that with this tool, we will be able to mainstream climate thinking. That's a little bit of jargon in the field, but simply we want climate adaptation and climate thinking to be everyone's business. So I could imagine all sorts of sectors that I think could use this. There's agriculture, there's stormwater planning, tourism, public health. I'm running out of things off the top of my head. Local municipal planners, municipal government, NGOs, a variety, wildlife conservation, anything you can think of, I think could get information that's relevant to them from this tool. The people we also really want to find are the decision makers. So who has the authority or who has contact to the authority to really implement this information and start making changes with it? Everybody has their own sphere of influence. Everybody has a place where they can start talking about climate change and getting people to think about it. And we want this information to get to those who are doing the planning and who are thinking about those long-term decisions. How should this tool be, let me click answer live. How should this tool be used in relation to the climate model projected data of the DNR Minnesota Climate Explorer? Will this tool eventually replace the Climate Explorer? It is kind of funny that we have Kenny Blumenfeld on this call as well. So Kenny, if you want to put in any comments in the Q&A, you're welcome to, and I'll read those aloud. The Climate Explorer was actually done with the previous generation of climate models. So that one was done with what is called CMIP 5, so the 5th generation of global climate models. It uses slightly different scenarios and has a different resolution. So the resolution of the data in that tool is about 6 miles, and the resolution of the data in our tool is about 2.5. However, that being said, you do not have to wait for new information and new data in order to start thinking about climate adaptation. In fact, we know today that the projections of climate models in the early 1990s were remarkably good at projecting what would happen with a doubling of CO2 in the atmosphere. And so you can start with the information that we have and use that to make long-term planning decisions. So we do not intend for MN CliMAT to replace the Climate Explorer. They are both usable tools. This one is newer generation, different scenarios, higher resolution. George Host asks, does growing season length vary across the state? Yes. So you have north to south gradients in growing season length. I don't have numbers off the top of my head, but also a kind of general trend, this is both within Minnesota and across the globe, is that climate change effects are more strongly felt in northern latitudes. And so you see that reflected in the observed changes of wintertime lows, that map I showed you way back at the beginning of the webinar. We're seeing a larger increase in those northern latitudes. And similarly, projected changes are expected to be larger at the northern latitudes. So correspondingly, you would expect the changes to growing season to be more drastic at those northern latitudes.
Okay, Susie, I think you made it through all those questions. I'm just watching the clock here. We've got about 5 more minutes. So if you have one more burning question for Susie, make sure you can enter it in the Q&A here. And Susie, I'll pass it back to you for any wrap up that you'd like to do before we do our final TPCC closing.
Thank you for the reminder, Madison. I would have missed my last slide, which would have been a mistake on my part. Let me go ahead and pull that up. So if you have any questions, first of all, we are rolling out a series of workshops that we are calling our Climate Adaptation Specialist Training Program, or CAST. So we're hosting a workshop on July 18th in Duluth. Please be on the lookout for that announcement from TPCC. In this workshop, you will learn not only how to use MN CliMAT, but how to make decisions about climate change in the face of uncertainty. It's beyond just learning how to access the data. It's how do we use the data in order to mitigate our risk to climate change. I also encourage you to look at our website for more resources related to climate change in Minnesota. And also, Madison, if you could drop those links in there for signing up for the MCAP newsletter. And I believe I also had details about the CAST program as a link in there as well. And if you have any questions, I'll go ahead and put my email in the chat. Please feel free to reach out to me with any questions about MN CliMAT, upcoming training opportunities, or specifically the workshop in Duluth.
Thank you so much, Susie. Really great overview about climate projections using the MN CliMAT tool, and great tee up and pitch for the workshop coming up in July. So I did drop all those links in the chat, and a reminder, we recorded this webinar today and we'll be following up with all the details about that day-long training and workshop opportunity just in a month from now. So that'll be a really exciting opportunity if you are interested in this topic and this webinar today got you thinking about climate projections and using them in your work. This training will be a really wonderful opportunity to learn more from Susie and other members of the MCAP team. So please join me in a virtual round of applause for Susie. And Susie, I don't see any more questions that come in. So thank you again. We'll make sure to share Susie's contact information in that follow-up email, but really appreciate your time and sharing this excellent tool with us all today here at TPCC.
Well, thank you for having me. Happy to be here.
Okay, more thank yous coming in through the Q&A. Yes, we all thank you for your time today. So thanks everyone, and we'll see you again at hopefully at our July training, if not our fall TPCC webinar or event, which will be announced through our Gov Delivery listserv. So take care, everyone.
Thank you.